So this lesson is on tangent lines. So what I mean by that is if I have a function and I have a point on that function, can I construct a line that intersects that in only one point? Now, what is that going to look like? It's going to well approximate the function at that point. Eventually, we'll call that an instantaneous rate of change. But that's the goal. That's what we're looking at trying to do here. So let's see what we can do with that. I'm going to pull up the function y equals x squared on Desmos. There it is. And I have 2 points of interest. I have the point 1, 1, and I have the point negative 2, 4. And my goal is to draw in the tangent lines. So what do I mean by that? Tangent lines? So I want to think about a line that intersects that graph in exactly one point. So it doesn't pierce it, right? And it doesn't come like this. That would intersect it at one point. But it well approximates it. That's what we're looking for. Same thing here at negative 2, 4, a line that will approximate the function tangent at that point. Think of it as kissing only that point. How do we find what that is? Well, for the sake of 1, 1, this is what that looks like. So that's what we mean by a tangent line. Now, it's hard to tell, but the only place where these two things intersect is at that point 1, 1. So how can I convince you of that? Or at least can I demonstrate that a little bit by zooming it in? So let's go ahead and zoom in at that point 1, 1. And you'll see the blue line is the tangent line, the red is the parabola. And the blue line is well approximating that. You see near that point, the behavior of the blue line is pretty close to the behavior of the red line. So that's going to define what we call an instantaneous rate of change. A slope certainly is a rate of change. Again, notice we keep zooming in. Notice we keep zooming in. Notice we keep zooming in. We keep zooming in. And at some point, it's very difficult to tell the difference between the blue tangent line and the red original parabola. But I want to find the equation of that blue tangent line. And I know what the point is. It goes through the point 1, 1. That's the only point it goes through. So the issue is, what is the slope? Can I find the slope of that blue line? That will give me the equation of the tangent line through the point 1, 1. Let's take a look at the point negative 2, 4 again. A tangent line well approximates it, hits it in one spot. And as we zoom in very close, the tangent line and the function should be essentially the same. So there we go. Here's our green tangent line. Let's zoom in very close. You can see now the green tangent line and the red parabola look pretty similar. As we zoom in even more, you can see they're indistinguishable. So the rate of change at that instant, that's how fast it's changing. The slope is the rate of change. So the instantaneous rate of change will be the slope of the tangent line. So what's our goal? What's our goal? Well, we want to find a tangent line at the point 3, 9. So there's the point 3, 9, and you can see it's almost a straight line already. But it's still bending. It's a parabola. It always bends. But what is the slope at that point? So I can pick another point pretty close to it, and I can see what it is and then find the slope between those two. So let's go back to 3, 9, and let's zoom in on it. I'm going to label it. So I have the point 3, 9 here, and I want to zoom in very much on the point 3, 9. You see it? So let's just kind of zoom in and zoom in and zoom in and, excuse me, I think I'm, yeah, so zoom in, zoom in, zoom in, zoom in, zoom in. Just a whole bunch of times. You can see the parabola looks basically like a straight line now. And again, Desmos doesn't care how many times I zoom in, but that's probably enough. So I have this point. If I find another point, now you can see this looks basically like a straight line. If I move off of this, Desmos is saying all of these are 3, 9. So I guess I zoomed in a little too far as Desmos is concerned. Probably still a little too far. That's getting better. I'd like a few more decimal places of accuracy. That's pretty good. Okay, why don't we go ahead and use this one? So I have the point 3.0065, 9.039. This came from zooming in very close to the 3.9. Notice it's 0.0065 away in the x direction and 0.039 away in the y direction. So what is the slope of that line? Let's look at those 2 points. The first point is 3.9. The second point is 3.0065 and 9.039. We want to find the slope. So what is the slope between those 2 points? Slope is y2 minus y1 over x2 minus x1. To get us ready for calculus, I prefer this notation, change in y over the change in x. Looking at our graph, from here to here, y goes up, from here to here, x goes up. So the change in y is positive, the change in x is positive, it's rising. The slope will be positive. Anyway, 9.039 minus 9 is 0.039. 3.0065 minus 3 is 0.0065. Remember, this is an approximation of our slope. So I'll pull out my calculator and see what I get. 0.039 divided by 0.0065. And my calculator gives me 6. Okay. So if that's the case, I believe the slope of the tangent is 6. Okay, so let's take a look. This is what we seem to have. These 2 points, it seems like the slope of this tangent is 6. So then, what is the equation of the line? Notice if I zoom it out, those 2 points essentially land on top of each other at this focus, at this zoom. But I think the point is 3.9 and I think the slope is 6. So let's put that together. 0.39. Slope is 6. It may be helpful to use the point slope form. Y minus y1 equals m times x minus x1. Y minus y1. Y minus 9 equals 6 times x minus 3. Which we can go ahead and graph that and see if that looks like it is going to be the tangent line. So we have y minus 9 equals 6 times x minus 3. And sure enough, that purple line looks like it well approximates that function near 3.9. So that if I zoom that thing in, that's my instantaneous rate of change as the slope is 6. So for a small change in x, the y has a change that is 6 times as big. The ratio of the change in y to the change in x is 6. So that'll give us an idea of velocity. So that's our tangent line. Our tangent line is purple, and our parabola was red, but you can't see at this zoom. You can't see, but once I go out, you can see the purple line is there going through both of those points, but again, at this zoom, you can't see those. So let's go ahead and draw all 3 of the tangent lines. There's the tangent line through 1, 1, and here is the tangent line through -2, 4. So you see the idea. Our goal is to find the equation of the tangent line to a function at a given point. So let's go ahead and do one more of these. So what's our goal going to be? This time I am going to say, let x equal sine x. Find the equation of the tangent line. Or find the equation of the tangent line, so we did on the other page. Find the equation of the tangent line, not y equals sine x. F of x equals sine x. Let f of x equal sine x, or y equals sine x. Find the equation of the tangent line. to the function at x equals pi over 6. Let's go ahead and draw that. Let's pick a point pretty close to approximate that and come up with the equation of our tangent line. So let's get rid of all of this. And we're going to take a look at y equals sine x, which looks like that. Let's adjust our window so that our step is pi over 6. And we have a little more y than we need. Let's just go, I don't know, -3 to 3. Okay, and we'll zoom that in. And now we can see it. So there's our point of interest, which happens to be pi over 6 1/2. The sine of pi over 6 is 1/2. So I'll go ahead and I will label that point on here as well. So pi over 6, comma 1/2. I want the equation of the tangent line there to that point. So I need to find the slope. I have the point. If I have the point, if I find the slope, then I can use the point slope form to find the equation of the line. So what do I want? Again, let's look at our original zoom. Here's our original zoom, or one of our zooms. I want to get something very close to this, another value, so that I can find the slope. So we're going to go ahead and zoom in 4 or 5 times till it looks virtually straight. Yeah, it looks pretty straight. We'll pick another point on here. Let's pick one. Sure, 0.5301. What was the y value? 5301 and 5056. Nothing special about this one. I just wanted to pick one that was close. So I have these 2 points that are close. And if I can find the slope between those 2 points, that should give me a reasonable approximation to find the slope of the tangent line. So our 2 points are pi over 6, 1/2. And the second point, 0.5301. And 0.5056. So what are we going to do? We want to find the slope. Again, we have our point, pi over 6, 1/2, find the slope. We know slope is change in y over change in x. If you prefer y2 minus y1 over x2 minus x1. So 0.5056 minus 1/2, which of course is 0056, divided by 0.5301 minus pi over 6, which gives me what? Maybe this is a good job for the graphing calculator. Let's pull it up. So up top we have 0.5056 minus 1/2. Divided by, on the bottom, we have 0.5301 minus pi over 6. And what is that slope that it gives me? About 0.861. Do we recognize that number from anything? Let's go with 3 decimal places, 0.861. Eventually, we will formalize this. But okay, so we have a slope here of about 0.861. So the slope is about 0.861, and the point is about pi over 6, 1/2. So using point slope form, y minus y1 equals m times x minus x1. We get y minus 1/2 equals m 0.861. times x minus pi over 6. That should be a pretty good approximation for our tangent line at that point, pi over 6, 1/2. So let's take a look, see if that's the case. Let's go back to our original graph. There's our original. Let's go ahead and draw what we think is going to be the tangent line. Y minus 1/2 equals 0.861 times x minus pi over 6. And boy, that looks pretty good. But I want to zoom in on it, and I want to see if indeed that's a good approximation, if that green line is a good approximation for the black function. Is it tangent? I'm going to turn off this second point for a minute because we're just having trouble seeing it. So again, the green line and the black sine function look like they're heading in the same direction. And if I zoom in enough, they will look essentially identical. Can I see that other point now? Sure can. So here's pi over 6.5, there's 0.5301, 0.5056. So that is our tangent line. So what this lesson is about is for you to understand what a tangent line is. It gives us the behavior of the function at that point. It will approximate that function in a neighborhood very, very close to that given x value. So we want to find the equation of tangent lines. This is an informal idea looking at values of the function. We'll do a more formal one next.